AWS Lakehouse Automation, loading and unloading data from Amazon Redshift using Apache Airflow. In the following video demonstration, we will learn how to programmatically load data into and unload data from Amazon Redshift using Apache Airflow. Since we are on AWS, we will be using the fully managed Amazon Managed Workflows for Apache Airflow, or Amazon MWAA for short. Using Airflow, we will copy raw data into staging tables, then merge that staging data into a series of tables. We will then load additional incremental data into Amazon Redshift on a regular schedule. Next, we will aggregate the data from several data sources and unload that data into an Amazon S3-based data lake. Lastly, we will catalog the data in S3 using Amazon Glue and query the data using Amazon Athena. Agenda. First, I will introduce the major technologies used in the demonstration. Then, I will describe the data source we will be using. Next, I will review the architecture used in the demonstration. I will also cover the prerequisites required to follow along with the demonstration, and let you know where you can find all the open source code used in the demonstration. And finally, we will spend the majority of our time hands-on in the actual demonstration. Technologies. Amazon Managed Workflows for Apache Airflow. Amazon MWAA is a highly available and secure, fully managed workflow orchestration for Apache Airflow. MWAA automatically scales its workflow execution capacity to meet your needs and is integrated with AWS's security services to help provide you with fast and secure access to your data. Apache Airflow. Apache Airflow is an open source platform to programmatically author, schedule, and monitor workflows. With Airflow, you author workflows as directed acyclic graphs, or DAGs, of tasks. DAGs are written in Python. Amazon Redshift. Amazon Redshift is AWS's petabyte-scale, fully managed cloud data warehouse. Redshift includes features like Aqua, the Advanced Query Accelerator, Redshift ML, data sharing, and Redshift Spectrum to access and query data in your data lake. AWS Glue. AWS Glue is a managed ETL service. AWS Glue data catalogs and AWS Glue crawlers, which we'll be using in this demonstration, allow you to discover and search across multiple AWS datasets. Data source. The ticket database is provided free by AWS. It is used in the AWS documentation to demonstrate Amazon Redshift. According to the documentation, this sample database application helps analysts track sales activities for the fictional ticket website, where users can buy and sell tickets online for sporting events, shows, and concerts. In particular, analysts can identify ticket movements over time, the success rate for sellers, and the best-selling events, venues, and seasons. The ticket database contains 7 tables, modeled in a simple star schema, with 2 fact and 5-dimension tables. The tables include categories, events, venues, users, listings, sales, and dates. On the screen is a schema diagram showing the relationship between the 7 ticket database tables. Architecture. On the screen you see a diagram which represents the architecture for the demonstration. In the demonstration, we will be using a series of Apache Airflow directed acyclic graphs, or DAGs, of tasks to programmatically load and unload data from Redshift. Each step in the diagram represents an Airflow DAG containing multiple tasks. DAGs are numbered 1 through 5. Starting from left to right on the screen, we have a single Amazon MWAA environment. The Airflow DAGs hosted in the MWAA environment require access to Amazon S3, Amazon Redshift, and optionally Amazon SNS. Access is secured through Amazon VPC endpoints. Next, we have a single Amazon Redshift cluster. Data is loaded, queried, and unloaded from Redshift. Redshift requires access to Amazon S3, which is also accomplished using a VPC endpoint. Next, we have AWS Glue, specifically an AWS Glue crawler to catalog the unloaded data into an Amazon Glue data catalog. To confirm the data was unloaded and cataloged correctly, we will use Amazon Athena. Amazon Athena is AWS's ad hoc query engine based on Presto. We will use Athena to query the unloaded data in Amazon S3. Lastly, we have 2 Amazon S3 buckets, one to hold all the Apache Airflow configuration files, DAGs, and SQL files. The second bucket will contain the raw ticket data that will be uploaded into Redshift. It will also hold the data unloaded from Redshift. As mentioned previously, each step in the architectural diagram represents an Airflow DAG containing multiple tasks. Here we see the DAGs in the Airflow UI, which we'll be using during the demonstration. DAGs 1 through 5 accomplish various parts of our demonstration. The 6th and final DAG sequentially executes DAGs 1 through 5. We will discuss each DAG as we move through the demonstration and look at the code. When the final DAG, DAG 6, completes, either successfully or unsuccessfully, an optional notification can be sent to Amazon SNS or Slack. On the screen, we see examples of successful and unsuccessful DAG notifications sent to a Slack channel via a custom Slack application I created and configured in Apache Airflow. Prerequisites. To follow along with the demonstration, you will need to create and configure the following AWS resources: Amazon MWAA environment running 2.x version of Apache Airflow, Amazon Redshift cluster, buckets used for the MWAA and Redshift files, security group ingress rules for Redshift from MWAA, VPC peering connection between MWAA and the Redshift VPCs, VPC endpoints, optional but recommended, Amazon Redshift enhanced VPC routing, optional but recommended, IAM roles and policies for MWAA, Redshift, and Glue, Amazon SNS topic for notifications, optional, DAGs, SQL files, and raw ticket data copied to the appropriate Amazon S3 buckets, variables set in MWAA for such things as the S3 buckets and the Glue and Redshift IAM roles and the SNS topic, Redshift configuration in MWAA. Source code. All the source code for the demonstration is open source and available on GitHub at github.com/Gary Stafford/ticket-data-lake-demo. The GitHub repository contains all of the Airflow DAGs, all the SQL statements, and the raw ticket data. Demonstration. Before getting started with the demonstration, let me review the files that I've already uploaded to Amazon S3 in preparation. You recall we have two Amazon S3 buckets. The first bucket, the Airflow bucket, contains the Airflow configuration files, DAGs, and SQL files, which are part of the demonstration. I've already uploaded the DAGs into the Airflow bucket. You can see those on my screen. There's 6 DAGs. In addition to the DAGs, there is a SQL subdirectory within the DAGs directory. Within the SQL subdirectory of the DAGs subdirectory are a number of SQL files. These files will be executed by the 6 DAGs during our demonstration. I've also uploaded the ticket data, representing the 7 ticket tables of S3. The data files have been gzip compressed to save transfer time and storage space. The data in these files will be copied into the staging tables in Redshift by Airflow. Also, before starting the demonstration, I have configured Airflow. I've created several variables containing values required by the DAGs as they execute their tasks. The variables include the names of the Amazon S3 buckets, the AWS Glue IAM role, the Amazon Redshift IAM role used to unload the data, and the optional Amazon SNS topic arm. I've also created 2 Airflow connections, the Amazon Redshift connection and the optional Slack connection. With all of these files and configurations in place, we can begin the demonstration. Airflow DAGs and MWAA can be triggered through the Airflow UI or using the AWS MWAA API. We will trigger the first 5 DAGs using the UI and the last DAG, DAG 6, through the API. Let me switch over to PyCharm and we'll take a look at the first DAG before we trigger it. The first DAG creates the ticket_demo name schema and 7 tables which will hold the ticket data in Amazon Redshift. The DAG uses the Postgres operator to execute a series of SQL statements contained in a SQL file. We can see that file here. I've set up 7 create table statements, 1 for each table that we'll be creating, and I've wrapped those in a transaction. That file will be called by the DAG. I've also created a list of 7 tables. We're going to loop through these 7 tables and create 7 dynamic tasks. So I've only defined a single task to drop table if it exists, and I put that in a loop, and it will loop through these 7 table names. I've also defined the schema, so ticket_demo is a constant schema. I'm going to loop through those 3 lines of code. So I have the Postgres operator, I've defined a single task with 3 lines of code, and I've put that in a loop. So we'll loop through and we'll make sure that we delete any existing tables. Because this is a demonstration, I want to make sure that those tables don't exist from previous runs of the demo. So I'm going to go ahead and delete those. The next task I'm going to run is a create tables. That will go and call the create_table SQL file, which is in the SQL subdirectory, which is in the DAGs subdirectory. So in my Airflow bucket, I have a DAGs directory. Within that DAGs directory, I have a SQL subdirectory. And within that subdirectory, I have the create tables SQL file. That will be called by this DAG. We'll generate 7 tasks. We'll run those in parallel to make sure that we've deleted any existing tables if they exist, and then we'll run the single SQL file. So let's switch over to the Airflow UI and we'll get started by getting the first DAG running in our demonstration. Let me open up the first DAG, and we can take a look at the graph view. Is probably the easiest way to visualize this DAG. So you can see on my screen we have these 7 drop table tasks. We'll run those in parallel. Once those 7 tasks complete successfully, we'll run our single SQL file, which contains 7 SQL statements. Those are create table statements, so we'll create our 7 tables that we're going to permanently store our data in Redshift in. So we'll go ahead and get that DAG started. I'll kick this DAG off. We don't have any additional configuration, so I'll trigger it directly. And this should finish relatively quickly. We can see that the SQL statement is run, and we're now at the end. So let me go into Redshift. Let's take a look and see what's been created. I have a single Amazon Redshift cluster set up for this demonstration in this account. You can see that cluster here. Let me open the query editor. So here's my Redshift cluster. I have several schemas in this Redshift cluster. We're going to be working with a ticket_demo schema. So let me open that up. And let's see if we have our 7 tables to begin. So we see that we have 7 tables. Make sure they're the right ones. Yep, so category, date, events, listing, sales, users, and venue. So those are our 7 tables, and we're going to be staging data and then loading data into those tables and then unloading data from those tables as we continue with the demonstration. Let me switch back to PyCharm. Let's take a look at the second DAG we're going to be running. So here's our second DAG. So the second DAG creates 7 staging tables, then uses the copy command to copy the data from Amazon S3 to the Redshift staging tables. This is done using the S3 to Redshift operator. Finally, the DAG uses a documented method described in the AWS documentation to insert the data from the staging tables into the regular tables that we just created in DAG 1. This is done using the Postgres operator. We can see here we have the S3 to Redshift operator and the Postgres operator. Last time I had a list of tables that we were using. This time I've created a dictionary. The reason I've created a dictionary is in addition to a list of the tables, which we'll be using to generate dynamic tasks, I also have the count of the number of rows that I'm expecting for data to be inserted into the staging tables and then merged into our permanent tables. I'm going to be using these counts along with the SQL value check operator to confirm that the file was successfully staged and then merged into our tables. I also have a begin date and an end date. So with DAG number 2, instead of loading all the data, for this simulation, we're going to assuming that we're running a monthly sales report. So we begin by loading the first month's worth of sales, and then every month we run DAG number 3, which is an incremental load to load the next month. So when we run DAG 2, we'll load February. We can run it again and run March, April, May, June, July, etc. So for DAG number 2, we're just going to load the January data into the staging tables and then copy that into the permanent tables. These are the counts and the number of rows that I expect of data. So if we take a look at the DAG again, we're using the same for loop, so for tables and table count.keys. So again, instead of having a list of tables, I now have a dictionary which has the table name and the row count. We'll be using both the keys and the values. So I'm looping through the keys, which are the table names. I'm creating my staging table. So again, instead of having 7 tasks, I have a single task. The only difference between this DAG and the first DAG is instead of having a single SQL statement that creates all 7 tables, I broke those staging tables up into individual SQL statements. Each one of the staging tables is in a separate SQL statement. So we see here the date underscore staging table, the event underscore staging table, etc. So I'll call each one of these individually, but we can still do that dynamically. So let me go back to the DAG. So you see here, I have the dynamic task ID, and then I have the dynamic SQL file that I'm calling, or SQL statement. In this case, it's a SQL file. So within the SQL subdirectory, I have named these so that I'm able to call these by simply changing the table name, which is contained in the keys of the dictionary. I'm then truncating those tables. So I'm creating those tables. If those tables already existed, I'm truncating them. I'm then staging the data from S3 to the staging table using the S3 to Redshift operator. So looping through again, generating 7 dynamic tasks. I'm reading in the raw files that I already had loaded into Amazon S3. So remember when we looked at that S3 bucket, I had 7 files, gzip compressed. This is the raw data that we're going to be loading in from S3 using DAG number 2. We're then going to merge that data from the staging table into the permanent table, and I'll show you one of those files. So let's look at the events. All of the files look very similar. I'll show you the events and then I'll show you sales, which sales has some parameters in it. So for 5 of the tables, there's no parameters. For the listing and sales tables, we're going to assume that as we do incremental loads every month, we're loading new data into the listing and sales tables. So for the event table, the data doesn't change. We're going to do 1 copy and 1 merge. We're going to get all the data in there one time, and then that will remain constant. The sales and listings tables will have incremental data on a monthly basis. So we'll rerun DAG number 2 once a month. We'll schedule that to load the new data in. Again, this is all just part of the demonstration, the simulation. So we have a begin transaction statement. We then delete any rows from the permanent table, so the non-staging table, where there's a corresponding row based on event ID in this case in the staging table. And then we're going to insert into the permanent table all of the rows from the staging table and then end our transaction. Again, this is one of the methods described in the AWS documentation. This is the method we'll be using. So once we've copied the data in from S3, we'll then be deleting any existing rows from the permanent tables, which exist in the staging tables, and then inserting the staging data into the permanent table using the same method. The only difference with listing and sales, if we look at listings, is we have some parameters. So remember that I said we're only going to load January data into the listing and staging tables, and then next month we'll load February, the month after March, April, May, June, July, etc. So for the initial load of data, we're just going to load January in. So we're going to assume that it's right now is the end of January of 2008, which is what the data is based on, and we're only loading in the January data. So the only difference between this file and the previous file that I showed you is there are some parameters. So this accepts the begin and end dates. It accepts it for both the delete and then for the insert. If we go back to our DAG, here's our begin date and our end date. So we're only loading in the two dates which I defined initially in DAG 2, which is January 1st through January 31st. We merge that data in, and then we drop the staging tables. We don't need the staging tables anymore, so we'll get rid of those. And the last thing I'm going to do to validate that this DAG was completed successfully, now the task can complete successfully, but maybe I've made a mistake, maybe I haven't created my task correctly, something's gone wrong which hasn't caused a failure of the task, but has not given me the results that I expect. I'm using the SQL value check operator, and I'm doing a select count from each table in that schema, and I'm checking that count against the dictionary that I showed you originally. So the table underscore counts dictionary has a count of the number of rows I expected. So for example, for the date table, I expect 365 rows. For the category table, I expect 11 rows. So I'm validating that each table has the expected number of rows, and if it does not, I'm going to fail. So you can see here I have tasks. I have 1, 2, 3, 4, 5, 6 dynamic tasks. Each one of these are going to create 7 tasks. So these dynamic task definitions, as I loop through these should create 7 tasks for each one of these 6 different tasks that I've defined. And we can see here my chain of tasks, which we're going to be executing. So let's switch over and we'll start DAG number 2. So I'll go back to the Airflow UI, go back out to DAGs. You can see here that I'm only showing the DAGs for this demonstration. I'm able to do that. If you're not familiar with the Airflow UI, you're able to add keywords to each DAG. So let me switch back to the DAG for a moment just to show you how this works. For other DAGs, you may have multiple tags depending on how you want to sort and organize your DAGs. But I have the Redshift demo, so I'm able to just query all of the DAGs and only show all of the DAGs. And in this case, I'll just show all of the active DAGs. I may have some DAGs that aren't active, or maybe I'm working on that are still being developed that I don't want to show. So I have 6 active DAGs, and each one of those have the Redshift demo keywords. So those are the only ones that I'm showing. That's how I'm able to filter down to only the DAGs for this demonstration. So that's quite helpful, especially if you have a lot of DAGs in your Airflow UI. So let's go into DAG number 2. So here's our second DAG. I think the graph view is probably the easiest thing to see. So we can see here that we have all of our dynamic tasks. So you can remember that we defined 6 tasks within our for loop. Each one of those 6 tasks are represented the 7 tables that we're going to be staging and merging into our permanent tables. You can see all those here. So we begin. We create our 7 staging tables. I'm creating a table if it doesn't exist. Whether it exists or not, I'm truncating it to make sure that if it's a new table or if it's an existing table, that it has no records in it. I'm then staging the data from S3 into the staging table, so loading the data from S3 from those gzip compressed files into S3. I'm then using that merge technique that I showed you in the SQL files, deleting the existing records in the permanent files if there are any, and then inserting the staging records into the permanent tables. I'm then dropping or deleting the staging tables. We don't need those anymore. And then I'm performing a QC check to make sure that I have the appropriate row count. So let's go ahead and start this DAG, and we should see that these workflows start in parallel. So 7 parallel workflows within the same DAG. And we do in fact see that they're starting. Each one of these 7 individual workflows are being completed sequentially. So one table is not dependent on another table. The task can be completed sequentially. They're taking different times to finish. So some tables only have 11 rows. Some have hundreds of thousands of rows. Some of those are going to complete more quickly than others. As those complete, we'll see those finish. We should see the end task turn green. And we do. So it took a few seconds. We went through and did all of that. And the best part about that is if you look at the number of tasks that are shown in our DAG, compared to our code, it's relatively simple. So we have about 100 lines of code, less if I take out all the spaces. So for something a little less than 100 lines of code, we've been able to define a fairly complex DAG that has 7 parallel workflows in it, and these workflows all complete in a number of seconds. So now if we switch back to Redshift, let me go back to my Redshift cluster. We have a Redshift cluster. Let me refresh that. We should not see any staging tables. So if our delete was successful, we should still just have our 7 tables. The difference being those 7 tables should have data in them now. So we do see 7 tables. So we created our staging tables if they didn't exist. We truncated them if they did exist for any reason. They were still around from processes maybe outside of our DAG workflow, outside of Airflow. Somebody created those staging tables out of band. We've truncated those. We loaded new data into those. We merged that data into these 7 tables, into the 7 permanent tables, and then we deleted those records. Now, I'm not even going to check to see if there's records in here because I know there are, because if I switch back to the Airflow UI, I did a row check. So let's look at one of these tasks in the row check. So I've clicked on the check row count categories, and we can go into the logs. And this task was successful. Let's look back at the DAG for categories. Categories should have 11 rows in it. So we ran a SQL test to a quality check, confirm that, in fact, the new categories table, which we created in DAG 1, which was empty, now has 11 rows in it. So I'm confident after running the series of tests using the SQL value check operator that all of my data is in my permanent tables. So let's move on to DAG number 3. Similar to DAG number 2, the third DAG loads incremental sales and listings data for the next sales period into Redshift. So remember that in DAG number 2, we loaded in all of the January data. So let's assume that it's now February and we want to incrementally load February in. So we're just going to do one incremental load for February, then we're going to move on and run the remaining DAGs. We're going to run this DAG, so we know that we already have January data, so we loaded any of the sales records, which were January 1st through January 31st. Now we're going to run a very similar DAG. This DAG is only going to load in the February data, so February 1st through February 28th. And you notice that for my list of tables, I only have listings and sales now. So the assumption for this demonstration is we have 7 tables. 5 of those tables have data which does not change throughout the course of the sales year. Again, this is a simulation. And the assumption is that the listing and sales data contain new data. So on a daily basis, on a weekly basis, on a monthly basis, there's new sales and listings being added to the tables. That information has been extracted, dropped into our data lake as compressed CSV files, and we're going to load those files into our tables. So as our analysts continue to do analysis using Redshift, they're getting the latest data. In this case, it's on a monthly basis. So you see the DAG is very similar. Again, the primary difference is we're only looping through 2 tables. So the first thing we're going to do is create our staging tables. Remember, we deleted those with DAG number 2. If they already exist for any reason, they were created out of band, we're going to truncate those. So we're either going to create them, or if they exist, truncate them. We're then going to use the S3 to Redshift operator in. We're going to load the listings and sales data only, the gzip compressed CSV files from S3, read those rows into our staging tables, and then perform the same merge technique, again deleting any existing records in the permanent tables that exist in the staging tables, and then loading those staging rows into our permanent tables as rows. So a very similar DAG to DAG number 2, the difference being we're only loading incremental data. So we're only focused on the month of February in this case, and we're only loading the data for 2 months into the data. And then again, we are doing the checks again. So we're doing a select count from the schema. And in this case, because the rows are different, I've used the SQL threshold check operator. So just to show a different check operator, I'm using the SQL threshold check operator. So I've defined the minimum threshold and the maximum threshold. I don't know how much sales data I have for the month of February. I could go take a look, but let's assume that we're running this on a monthly basis and that number is going to change. So I've made some assumptions. I'm assuming that the minimum number of sales we made in any month is 1. If there's not at least 1, if there's less than 1, if there's 0, that could point to a problem with the data. So I want to make sure that if there is no data that I'm alerted, so this DAG will fail. I'm also making the assumption that the maximum number of sales in any month is 100,000. Based on the average number of sales so far, 100,000 is a multiple of the expected number of sales. If I see more than that, that might be a sign that I loaded too much data. This is just a demonstration. Somebody who's more familiar with the data would have to define those numbers. I'm just using 1 in 100,000 for this demonstration. And again, we're using the SQL threshold check operator, and we're doing a select count from each one of the tables, and we're making sure that the number of new rows that were inserted into the tables for the month of February, so the sales and the listings which contain a date which falls within February, is somewhere between 1 and 100,000. So we'll go ahead and run this DAG. I'll switch back to the Airflow UI. We'll go into DAG number 3 and take a look at it before we trigger it. We'll go to the graph view. And we can see here, so somewhat of a much simpler workflow than DAG number 2, which had 7 parallel workflows in it. This one has 2. So create tables or truncate tables for staging, for listing and sales, stage the listing and sales data for the month of February, merge that data into the existing table. So we already have tables. We have 7 tables, and they already have January data in those for listings and sales. We're going to merge in the February listing and sales data, so add that to those tables. So now we'll have January and February sales, and then we'll drop the staging tables, and then we're going to run our 2 checks. And I could have run these in parallel. They're run sequentially. There's no reason I couldn't have also ran these in parallel. So let's kick this DAG off. Again, this DAG should run pretty quickly. Although this demonstration is talking about big data, usually Redshift is associated with big data. Obviously, these are not big data sets, which saves time and money. You'll be able to run this demonstration yourself and not either take a lot of time or spend a lot of money on AWS. So I've kept the data sets pretty small, so these run pretty fast. Obviously, if these were millions or billions of rows, you would expect them to run a little longer. But since we're only loading in 1 month of data in relatively small data sets, they run pretty quickly. So we can see a few seconds it took to run that DAG. They've completed successfully. If I were to go back into Redshift and again and check to make sure that my tables were deleted, I'm confident they were deleted, and I'm also confident that the number of rows within the tables is correct, and I'm not going to check that. I could run a SQL statement to check that, but I'm confident in my check. So again, if we go into our quality check here, do you remember that we counted the number of new sales records for the month of February? So we can see that that test ran. We ran our query statement. Remember, we had a threshold of 1 and 100,000, and the result was true. So the number of sales, the exact number doesn't matter, but the number of new listing rows and sales rows in the month of February, which was loaded into the Redshift schema, is somewhere between 1 and 100,000. So based on that, I should be confident that everything worked. So we'll move on to our 4th DAG. The 4th DAG joins and aggregates data from several tables and unloads those results into Amazon S3. We have a fairly complex query that we're going to execute. The exact details of the query really don't matter. Really what we're trying to simulate is the unload. So you can see here I've opened the SQL statement. It's an unload statement. We're using the unload SQL function. And I've written a SQL statement. Now again, the exact details of what this doing isn't really important. You can see though that there is a left join. We're joining several of the tables. 5 out of 7 tables we're joining data across those tables, running some basic functions, rounding, casting, doing some basic functions to that data, creating a final data set. So let's assume that this is a final data set that we're going to expose to our data analyst. So our data analyst may not know all of the foreign and primary key relationships between these tables. Maybe they don't understand how to join those properly. Really what they want is a final aggregate look at the sales, which they can perform further analysis on. So using this query, we're going to create that aggregate sales view that we're going to expose to our analyst. So we query that data and then we unload that data. The bottom of the SQL statement you see 2. So where do we want to unload that data to? What is the S3 path? What bucket? What object prefix do we want to unload that data into? An IAM role, so I have to define an IAM role. Who has access? What role has access to export or unload this data from Redshift into S3? So we need access from Redshift into S3. And then what is the format of the data you want to unload? In this case, I'm using Parquet, so Apache Parquet format, columnar format, very effective and efficient for analytics queries. I'm also partitioning that data. So I'm assuming that when my analysts query this data, their where clause, how they filter this data, most commonly they're filtering it on the category group and category name. So I'm partitioning the Parquet data by category group and category name. It will be much more efficient and effective for them to query the data using those predicates. What isn't in here, but by default, the Parquet data is also snappy compressed. So we're querying the data, we're unloading the result set of that query into S3 as partitioned, compressed Apache Parquet format files. So let's go ahead and run DAG number 4. I'll go back into the Airflow UI. I'll go into DAG number 4. We'll take a look at the graph view before we run it. So the simplest of all the DAGs that we're going to be running, it only has a single task, the unload sales data. That will run our SQL statement. When I'm done with this, we'll take a look in S3, and I would expect to see partitioned Apache Parquet format files in Amazon S3. So let's trigger this again. No additional configuration needed. We'll go to our graph view. Even though that was a fairly complex query, we're talking about hundreds of thousands of rows at most, not millions or billions of rows, so it runs pretty quick, a few seconds. That's completed successfully. So let's go over to S3 and take a look and see what we have. So I'm going to go back out. So this was my original raw data, my gzip compressed files, which is what we loaded into our staging tables originally. If I go back out to Redshift, I see that I now have a sales key or sales subdirectory, and I can see that I have cat groups. You remember that we partitioned the data by category group and category name. So category group, we have concerts and shows. So it looks like it worked. If I go into shows, the category group of shows, I now have 3 category names: musicals, operas, and plays. So again, it looks like everything worked. Let's just randomly go into plays. And I see 2 Apache Parquet format files. So it looks like everything works. So if we switch back to PyCharm for a minute, recall this was our unload statement. So we ran this SQL statement. The result set of this unloaded into Amazon S3 as snappy compressed Parquet files partitioned by category group and category name. And that does appear to what we have as a result in S3. We can take a look at one of these files. Let's just take a look and make sure that the data looks correct. So I've clicked on one of these files or one of these objects, and we can use the query with S3 select function in S3. We know we have Apache Parquet. Let's view it as JSON. And we'll just look at the first 5 objects. So within this object or this flat file, within this Parquet file, we'll look at the first 5, let's call them rows of data in Parquet. And we can see that it looks like what we were expecting. So the results of that query should have returned the price paid, the quantity sold, the number of tickets sold, the total sales amount. So in this case, 269 times 1. The commission, the amount of commission paid, the percentage of commission paid, what the event was, who the seller was, and who the buyer was. So this looks correct. So DAG number 4 was successful, and we can move on to DAG number 5. So let me switch back to PyCharm for a moment. Let's open DAG number 5 and take a look. So the 5th and final DAG in the demonstration catalogs the unloaded data in Amazon S3 using AWS Glue. So we're using the AWS Glue crawler operator. Once that data has been crawled and cataloged in an AWS Glue data catalog, we're then using Amazon Athena to query the data. Again, this is a type of quality check. All I want to do is make sure I can query that data. If that data were not cataloged properly, if the catalog did not exist, if the table did not exist, if for some reason it was not cataloged correctly, then the Athena query should fail. So again, I'm only using Athena here, one to demonstrate that Airflow can in fact work directly with Amazon Athena through the operator, but also as a quality check. So the assumption here is that we query the data. You remember our unload SQL statement, that data set is a data set we're going to expose or provide to our data analysts, right? That refined silver or gold data set that the data analysts are going to use for further analysis, for visualization, for business intelligence. Maybe they're going to be building a machine learning model on that. I want to make sure that that data is available. Now, the fact that it's in S3 doesn't make it available. What makes it available, at least in AWS terms, is having an AWS Glue data catalog, which is a Hive-compatible metastore, and I've cataloged that data in the AWS Glue data catalog. Using Amazon Athena, I don't query S3 directly. I query the data catalog table. The data catalog table has the schema and metadata information about the underlying data in S3 that we unloaded. And through the AWS Glue data catalog, I'm able to return the data from S3. I need to crawl that data. I need to catalog that data, that unloaded data. And then I just want to confirm using Athena that I'm actually able to query it before I turn it over to my data analysts and they have a problem with it. So I want to confirm that that data is queryable. So again, we're using the AWS Glue crawler. I have not created my crawler ahead of time. You can create your crawler ahead of time. You could use Terraform or CloudFormation to create your AWS Glue crawler, your AWS Glue data catalog, your tables. You could define all of that ahead of time. And generally in production you would. But in this case, for this demonstration, we'll create my crawler dynamically. So if my crawler doesn't exist the first time this runs, it will create my crawler. If I change any of the parameters within this task, in this AWS Glue crawler operator task, that will modify the crawler if it already exists. I haven't changed any parameters in here. It'll simply run it. So it's a fairly useful operator. It will create a crawler if it doesn't exist. It will modify an existing crawler if the crawler exists but you've changed the parameters. And if the crawler exists and the parameters are the same, it will simply start that crawler. So I don't have to worry about having that crawler ahead of time. If I make any changes here, I'm confident that we'll update that crawler to my specifications. And I'm confident that every time I run this DAG, if the crawler exists, it will run that crawler. I'm using the bash operator with the AWS Glue CLI, so the same as executing it from your command line, and I'm doing an AWS Glue delete database. So if that AWS Glue data catalog, referred to as a database from in the CLI, in the API, I'm deleting that database, and then I'm creating a new one. So I have a fresh AWS Glue data catalog. I'm then creating my crawler if it doesn't exist. I'm running my crawler. I'm crawling the data in S3 that I've unloaded from Redshift, and I'm cataloging that into the AWS Glue data catalog. And then I'm just running another quality check. So one way to run a quality check, you can use a bash operator. It's not as effective as using a specific operator for an AWS service, but it also gives you the ability to work with any AWS service because you're using the bash operator with the AWS CLI. So I do an AWS Glue get tables, and I want to make sure I list those tables out, and I can check the logs to make sure that it created a single sales table, which is what I'm expecting. And then lastly, we run our Athena query. So again, just a very basic Athena query. It doesn't really matter what I query. What I want to know is, can I query the data that's been cataloged in AWS Glue Data Catalog? Here we're doing just a select star from the sales table. The sales table is the table I'm expecting to be in the AWS Glue Data Catalog. And I'm also just running a where clause. You remember that we partition the data by category group and category name. So I'm just doing shows opera to make sure that those exist. And just returning 10 rows. The number of rows returned really doesn't matter. All I want to know is, does this query work or does it fail? If it works, we're all good. We're done with our demonstration. If it fails, then something went wrong in the process. Either the data wasn't unloaded correctly, the data wasn't cataloged correctly, the data is not in the proper format that I expect. So hopefully this answers that. And then I just return that query to an S3 location. You have to give it a location to return the query results to. But again, we're just worried whether this task fails or succeeds. So let's switch back over to my UI and we'll run our last DAG here. So DAG number 5. And let's just again take a look at the graph view. Pretty simple sequential series of tasks. Delete the demo catalog if it exists, so the AWS Glue Data Catalog. Create a new AWS Glue Data Catalog. No tables, just an empty catalog. Create, modify, or start the crawler depending on what state it's in. Let's assume there is no crawler right now. It's the first time we run this demo, so it'll create the crawler. It will then run the crawler. That's going to take a few minutes, so I'm going to pause the demo as we get to this stage. Probably take 4 to 5 minutes to run maybe the first time. Once that crawler's done, we're then going to just list out in the logs the glue tables. I'm expecting to have one sales table. Once that task completes, we're going to run our Athena query just to make sure that that data is queryable. We're going to kind of simulate what a data analyst would do with the data to make sure that it works. And if everything works, we'll end that DAG successfully. So I will trigger the DAG. Again, no additional configuration needed. We'll go to the graph view. Just make sure that the DAG starts properly. So we've deleted any existing catalog if one existed. We created a new one. The crawler is going. I'm going to pause the video. Again, this might take 3 to 4 minutes to finish the first time, so it's creating the crawler right now, and then we'll start that crawler. Once that crawler finishes successfully, list the tables, and the Athena query should only take a matter of seconds, and we'll look at the results. So we can see that the glue crawler has completed successfully. The glue crawler task has completed successfully, I should say. The list tables has completed successfully, and we're just waiting for the Athena query to finish successfully, making sure that we can query the results that were cataloged. And we can see that the Athena query task completed successfully, and the task has ended. So we can see the results here. Everything looks good. Let's just look at the list table for a minute in the logs. We should see a single table. Again, not necessarily a quality check that will fail, but just informationally I can go into the logs and make sure that I can see the tables that I expected. So that looks good. And if we look at the Athena logs, the Athena operator logs for this task, we can see that that also completed successfully. Let's switch back. I've opened the AWS Glue Console UI. I'm in the Ticket Redshift demo database, so the AWS Glue Data Catalog, Ticket Redshift demo. That's the new AWS Glue Data Catalog that we created. Let's list the tables. So we see one sales table. We can see its location is S3, so that's where our sales data was. You remember in S3, we viewed this file that was in the Redshift sales subdirectory. In the console, we can see, in fact, that that's where the data has been cataloged, so that's good. We can see that it's Parquet format. That looks good. Let's just take a look at the table and make sure that this looks correct. So we can see here record count. We have 20,892 records or rows in there, has average row size. That looks good, so there's definitely data in there. There's sales data in there. That sounds about right, just knowing the number of sales that are generated each month. And again, this is the sales table, so you can remember we originally loaded the month of January. Then we ran DAG number 2, which incrementally added, DAG number 3, which incrementally added the month of February to the January data. So that number looks right. We can view partitions. So we see we have the category group partition and the category name partition. So shows, concerts for category group, and then opera, plays, pop, and musicals for the category name subdirectories or subpartitions. So that all looks good. So I think everything worked, and we know that the Athena task completed successfully. So we're all done with our demonstration. We ran through our 5 DAGs as part of our demonstration. They were all successful. DAG number 1 created our permanent tables in our ticket_demo schema within Amazon Redshift. We then created our 7 staging tables. We loaded the initial data into those tables. So for 5 of those tables, that data didn't change throughout the demonstration. For 2 of those, we have some incremental data that we loaded in a later DAG. So we loaded in the month of January for listings and sales. We merged that data into the permanent tables using the documented AWS method. We then ran DAG number 3, which incrementally loaded the sales and listings data for the month of February. We then unloaded that data, so we performed a fairly complex SQL query, a join across 5 of the 7 tables that we loaded data into, did some simple calculations, some SQL functions, took that result set, wrote that to Parquet format, snappy compressed, partitioned data in Amazon S3. We then cataloged that unloaded data with an AWS Glue crawler into an AWS Glue data catalog. And then we performed a simple Athena query on that. So using AWS's ad hoc query engine, Amazon Athena, to perform a query on the data. The query was executed against the AWS Glue data catalog table that returned the underlying data in S3 to Amazon Athena. So that all worked. That data set is now available for our data analysts. On a monthly basis or daily basis or a weekly basis, we would just run this incremental Redshift. In this case, it's set up for monthly. So at the end of every month, we could schedule this task to run on the last day of every month at midnight, let's say. That will load in any new sales and listings data, and that data will be available for our data analysts. We'll run the unload command again. That will create a fresh set of data with the new sales amounts for that month. We'll then catalog that data and we'll test the query. So at the beginning of every new month, that data from the previous month will be available for our data analysts, and we can automate all that through Redshift. We can schedule DAGs 3, 4, and 5 to make sure that on a monthly basis that we have data available for our data analysts. And again, that could be monthly, it could be weekly, it could be daily, it could be hourly, it doesn't matter. In this case, we're just using the example of a monthly sales report. So all 5 DAGs have been run successfully. You recall there's a DAG number 6. DAG number 6 is an example of a DAG which runs other DAGs. So in and of itself, it really doesn't perform any special functions as part of this demonstration. The purpose of this DAG is to run the other 5 DAGs which we already ran. So again, this is a simulation. Quite often, I just want to run all 5 DAGs. I want to create my permanent tables. I want to stage the data into my staging tables. I want to merge the data into the permanent tables. I then want to query that data and unload that data into S3. I then want to catalog that data with Glue and run an Amazon Athena query. So I want to do all of that every time as part of my demonstration. Now, in real life, you wouldn't run all 5 of these DAGs. DAG number 1, for example, creates the permanent tables. That's a one-time run, right? You run that DAG, those tables are created. Now, if you have multiple environments, you would run that DAG once for each environment. But realistically, DAG number 1, you would only run one time. For the sake of the demonstration, quite often I want to run all 5 of these DAGs. What this DAG demonstrates is the ability to run external DAGs as part of a DAG. This DAG can run other DAGs that are in my Airflow directory in Amazon S3, which have been loaded into Airflow. I can call any of those DAGs from this DAG. If we go back to PyCharm for a minute, let's take a look at this DAG. So how do we do that? How do we run these DAGs? I'm using the trigger DAG operator. The trigger DAG operator triggers these DAGs. So again, this looks very similar to my other DAGs. The difference being I've defined a trigger DAG operator. Now I've not looped through these. I could have done that, but I do also want to run these sequentially. So I don't want to run these in parallel. I want to run these sequentially. So I want 1 to run and complete successfully, then 2 to run and complete successfully, 3, 4, and 5. But I want to run the DAGs sequentially. So I've defined each one here. Instead of using a loop, I've defined my 5 tasks. So trigger DAG 1, trigger DAG 2, trigger DAG 3, trigger DAG 4, trigger DAG 5. And then I've chained those together. So begin, trigger 1, 2, 3, 4, and 5, and end. And I've defined a task for each one of those. The other thing that DAG 6 contains is a notification. So that's something we haven't talked about before. Quite often with your DAGs, you want to alert, whether that's an email, an SNS topic, or Slack. You want somebody to know that the DAG has finished successfully, or more often you want to let somebody know when the DAG has failed. Or you want to let a system know that the DAG has failed so it can take some action. In this case, I've defined 4 tasks. So I've defined a failure notification and a success notification for SNS, for simple notification service. This can send a notification on a success or failure to Amazon SNS. I've also created a custom Slack application, and I've defined a Slack failure notification and a Slack success notification. I can send a notification on a failure or success to SNS in this case, or Slack. There's many other options. I just chose those 2. And you can see here, when I define my DAG, I've defined the on failure callback method and the on success callback method. In this case, I'm using the Slack failure notification and the Slack success notification that I've defined. I could have also done SNS. We could do email. There's a number of options there. SNS and Slack are the 2 that I see most often. So we've defined those. And what will happen is when this DAG completes, whether it fails or succeeds, succeeds, a notification will be sent to Slack in this case. So this DAG has an example of not only running external DAGs from this DAG, it also has examples of either sending a notification to SNS or to Slack. That's the end of our demonstration. I'm not going to run this. This would take several minutes to run. Again, we've already seen each one of these individual DAGs be triggered and succeed successfully. I would expect nothing less to this, but again, a demonstration of how you can run external DAGs and also an example of how you can send either failure or success notifications to a number of different endpoints. Thank you very much for your time.